That was a short 10 minutes for me. I didn't realize it was 10 minutes since I started this. Purplish, what's up? Redeeming that first. Chasing that internet fame. Hey Kinran, how are you? Hope you're well. It is... I don't know. Teeny hasn't been around this week. I'm guessing he's busy with school and stuff. He's working on a master's. So, you know. He's been a little bit busier of late. Giving him grace. Last time he didn't show up for 2 streams, I messaged him and just like, so did I screw up, or like are you okay? Did I say anything terrible? And he's like, no man, I just started, you know, like uni started again in Germany. I wasn't probably supposed to. Oh well, yep. Sorry Teeny, if you hear that, but or some country, and you know, busy. Classic me leaking information. But yeah, let's see. I decided to leave. We're gonna let our binary search tree rest a little while. I think we ended up with 8 streams of binary search tree, technically 9, but I didn't publish one of them because we did like nothing, and I scrapped the entire thing. I scrapped everything that I did, but yeah, that's okay. I didn't feel like publishing that one. I struggle enough already in general, but yeah, I don't know what teenies think, and Master's more important than Twitch. Yeah, good deal. So we're gonna get started, I think, on a Min Heap today. It'll be interesting to see how this shapes up. And there's something I'm forgetting. 2 things. I need to... Time to learn some... I should turn off my starting soon thing. I forget to do that sometimes. Okay. Time to learn you some priorities with a priority queue. It's only barely visible. It's like the largest thing in my whole stream was the starting soon thing. Yeah, it's all good. Time to learn you some priorities with a priority queue, aka Min Heap. Technically Max Heap, you know, it's still priority queue. Just depends on your priority, I guess. In Rust. But now you can see Balmer. It is hilarious, like, because I don't do a lot of images, that he's probably going to be there for a long time. Alright. We did the Twitter posting. So we should be able to get to... I didn't turn on a certain light. Let's do that. It usually helps a little bit, I think. Makes my face just that much brighter. Yeah, so let's see here. Oh, did somebody like something that I posted? Let's just see. Gotta follow Anna Ritchie. How about it? All right. Let's hide Twitter from ourselves now so that we don't get distracted. And let's close out our binary search tree. We don't need this open. Okay, here we go. What do I want to call this? I could call it priority queue, or I could call it Min Heap. What do I want to do? I guess we'll just call it a priority queue. Why not? Let's see. PQ, right, yeah. P comes before Q. Am I implementing these just to implement them? Yeah, pretty much. That is the case. That's the idea, just for fun. Kind of get the data structure, like reinforce the knowledge of data structures, reinforce concepts in Rust as we go along. That's the idea. Yeah, some of them. Yeah, we looked at like how Vec is done, and we haven't gone back and looked at how a lot of these other ones are done. How confident am I feeling with Rust at the moment? It's like what's a good way of explaining it? A curve, right? Like an infinite curving graph, like a wave. More like a sound wave, you know? So at the moment is very important part of that question. I don't know. I mean, I feel like if I was put into a project and I needed to figure things out, I could figure things out without much effort. I actually was thinking about this the other day. How I would explain it is before I started working with Clojure for my day job, I spent, let's see, I don't know, probably 6 months before that, I learned a little bit of Clojure. Went through the first few chapters, I don't know, 4 or 5 chapters maybe, of the main Clojure book. I can't remember what it's called. It has some, you know, quirky name. So I spent like, you know, a couple weeks maybe playing around with Clojure. And then the week before I started my Clojure job, I like re-went through that entire book. Brave Clojure, that's it. Yep. Clojure for the brave and true, or something like that, right? Something like that. Let's see. And then, you know, so I did that, and then I spent my first week on my job working in Clojure, of course. I would say after 3 months of a lot more intense learning of Rust, I'm pretty close to that same point. So it's kind of like it's what is that, 12 weeks? So like 4x learning curve, you know, something like that over Clojure, which makes sense. Clojure is very simple. So pretty funny. But yeah, I think that's the best way I could phrase it. Yeah, it is a bit unfair for us. It's probably a bit unfair for us. I mean, in the sense that, yeah, I mean, I don't know if I've ever gotten into a language as quickly as I did Clojure. It's just it's so dead simple. When you get, as long as you're not tripped up by, you know, the fact that it's a Lisp. Like, other than that, like, if like some people's brains literally just like melt at the sight, as you know, since you write Haskell, Kinran, like people's brains will melt at the sight of anything that's not C style syntax, right? I didn't have that problem, so you know, it's just a very fast language to get into. Yeah, exactly. Yeah, the JVM's easily the worst part of Clojure, in my opinion. Easily. I've been thinking about doing... Hey, Alvi. Thanks for joining. Yeah, we're doing good. We're about to get started on a priority queue. We were just talking about, like, learning languages. And I was saying that so far I think Rust has about a 4x learning curve over Clojure, which is again a little unfair because Clojure is so simple. So it's probably even more than that. But or you know, unfair to Rust. Yeah. But I don't know. It might even be more than that. It's also hard to compare. Whoops, I clicked on my browser. It's hard to compare also because it's like my level of general engineering understanding, development understanding 5 years ago is a lot less than my level of development understanding now, right? At least I certainly hope so. Easy getting higher jobs, that would be JavaScript / TypeScript and or PHP. That would be the main things I would say, for sure. I would say most jobs are in that realm. I think I forgot my phone in the other room, which is not going to bode well for quick message checks. So I'm going to go grab that. Talk amongst yourselves. I'll be right back. Phone has been found. We're good. Let's see. Let's see if we have anything we need to respond to real quick. Okay, cool. That's all good. What do I think about Ruby? I mean, it's another easy, simple language. It can be a great entry point for people. I think outside of, like, it just depends on what you want to do. If you're going to go into Ruby development, you're probably going to be full stack. If you're going into JavaScript, well, I mean, pretty much all those, you're most likely going to be full stack. If you really enjoy that, that's cool. It's possible you could get a Ruby job being more back-end focused than not, but I don't really know what Ruby folks are doing these days. You know, I don't follow it very closely. It's not a language I ever learned or an ecosystem I ever really followed much. But yeah, I mean, there's a fair amount of Ruby jobs. I'd say there's a lot more JavaScript jobs. Also depends on where you live in the world. I think just like looking at job boards and seeing what people are looking for, that's always good. Yeah, Elixir is definitely growing in popularity in a lot of places. Yeah, which makes sense. It's Nice platform, for sure. Yeah, I have a buddy who works in Elixir. He actually works for an embedded company that does some Elixir for embedded, and then all their other kind of like web services are all written in Elixir. So, pretty cool. Okay. Well, did we actually create our file yet? Probably not. Here it is. We're gonna need the dead code warning off. I already forgot the syntax. Very good at that. Let's just borrow it from here. There it is. Okay, so let's define what our priority queue is. Actually, we'll do that one. Priority queue. What games do I play? I don't play that often. I go through different spurts on what I'm interested in. I've played quite a bit of Minecraft, actually. I have a kid, and so that's part of it. I mean, she's 14 now, but she still likes Minecraft, so that's cool. Very cool. Very cool of her. So we'll play that sometimes. I have a Switch, so I'll often play games on that. I like Breath of the Wild, pretty good game. Rune Factory 5, kind of like a silly anime game. I've been enjoying that. And then I play this like kind of like Minecraft inspired survivalist game called Vintage Story, which has been a lot of fun. It actually works on Linux, even though I don't play it on Linux. I play it on, because my gaming box is a Windows box anyway, so I played it on Windows. But, well, my gaming box is actually an old work computer. That's a MacBook Pro, like a 2018 probably, 2017, 2018, one of those. MacBook Pro Intel based, and I installed Windows on it using Boot Camp. And it has, like, you know, a nice processor, discrete graphics card. You know, I mean, it's aged at this point, but for the games I like to play, it'll play pretty much any of them. So technically my gaming box is a MacBook running Windows, but yeah, pretty funny. Because of how bad like OBS works on Intel-based MacBooks, like it works a lot better on Windows, on silicone MacBooks, and on Linux. Like, and it's not OBS's fault, actually. It's actually Mac OS's fault. I won't go into that whole thing, but basically Intel-based MacBooks, the Mac OS on Intel-based MacBooks does not support hardware encoded constant bitrate streaming, which is basically required for Twitch. So I have, despite the fact that I have a decent discrete graphics card, I have to do everything software encoded for my stream, which is a lot more intensive on the CPU, of course. But no, I didn't take computer science. Yeah, nope. I have an unfinished master's in philosophy, though. Very helpful, very helpful. Yeah, I started. I mean, I was always kind of like nerdy, techie growing up and stuff, but did different things. played around with websites, JavaScript and stuff like that. Built computers when I was a teenager and sold them for profit. And did those kinds of things. But yeah, I did a bunch of stuff in my 20s. And then when I was about, I guess I was around 26 is when I decided to 26, 27. I decided that I could actually make, you know, coding a profession, and I knew it would pay well, and I was kind of broke. And so I did. Yeah, took me about 12 months of studying and stuff until I got my first job. Market was also very different back then. But my undergrad's in religious studies. Yeah, fun times. Priority queue. Okay, so let's talk about what a priority queue is. We will say, oh, I'm using Emacs commands. I'm like, why is this not working? It's because I'm in Vim mode. Okay. AKA Min Heap. And let's talk about this. So basically, this is a tree-like data structure. Let's call it a binary tree-like data structure. I'll get back to your questions in a minute once I finish my thought here. Binary tree-like data structure has heap condition and so the heap condition in Min Heap. Yeah, Kinran, thanks for dropping in. I appreciate it. Have a good one. And Min Heap, the heap condition is that the every node under current node, let's see, is larger, right? So similarly in max heap, every node under current node is smaller. What do we actually care about? We care about being able to take off the smallest node, so basically the root. So we need to pop off or pop the root. I'll have to look up what a good name for that is. I don't actually know what the standard name for taking the root from a priority queue is. But you need to pop the root. You need to push to the next, push to the bottom, basically. And that's public. And then this bubbles up to find correct place. That's more of an internal implementation detail, but basically popping the root and pushing to the bottom should both be constant time. Okay, anything else I feel like I need to specify here? I guess that's the other thing. We'll put it up here. and that's that it is balanced. Which is to say that one branch is going to be much larger than the other. At most the height difference of nodes will be 1. They're browns. Yeah. They're browns. MX browns. It's like a 7 or 8 year old keyboard at this point. Pre-built. I didn't do anything to it. I like it. I mean, I know keyboard aficionados aren't as much of a fan, but you know, they do a lot of crazy things like lubing and foaming and all this other stuff. It works for what I use it for. Okay, I think we have our basic idea of a priority queue done. Yeah, they do get a bad rap. I don't really know, because I don't know. I don't consume all that much content, to be honest with you. It's probably only like 4 or 5 months ago that I actually started consuming content again, like regularly, from just like internet and stuff. Oh, that just means like people speak bad about them, like they have a bad reputation. Actually, rap is a good like bad rap kind of means like bad reputation, or people talk bad about them. Yeah. I like it. It's an Ergodox Easy, you know, split keyboard. Has some factory tinting built into it. Eventually I'll get a keyboard cam. I just haven't felt like spending the money you know, to get another camera. I don't have another camera just sitting around, so I'd actually have to buy one. What, the keyboard? The keyboard was, yeah, it was not expensive. I mean, it was not cheap. You know, it's about, but I mean, a pre-built split mechanical keyboard is just not cheap in general. It'd be expensive regardless. I'm pretty happy with it though. I mean, I'm ready for something new probably in the next year. I've had it kind of a long time and I want to try out something else, but we'll see what happens. Okay, so there's our priority queue. Let me go back, and I think you asked me a couple questions. Just one that I didn't answer. How did you get your first job, and how long after starting learning did you get it? I mean, it's a really hard question for me to answer. Because I mean, technically I started when I was 13 building websites on GeoCities, you know? That was the first thing that I learned programming for, you know, programming, right? I built websites for a few companies when I was a teen using jQuery, and you know, whatever, figured out a way to host them. I don't remember, we probably just GeoCities, not tripod. Yeah. And then well, I was 13 how many years ago now? I guess that's 25 years ago. It was a while ago. And then I played around with different JavaScript stuff, like just for fun little projects, like in my 20s. Got a little bit back into it just to do fun stuff, and just random jobs that I did might use them. Did some different consulting stuff, and I used JavaScript to do a few things for that, even though like the job wasn't coding. But like it was 12 months from the time where I was like, okay, I'm going to start a tutorial on learning on coding, you know, an app, a web app. It was about 12 months from when I decided that, and I had my first job. The market was different. If I had a hard technical interview, I wouldn't have passed it at that point. I mean, I might not pass it still. But that's just depends. Like if you're talking about like a thing, whatever, manga interview type of thing. You know, I don't know. I have mixed feelings about those. So, yeah. But yeah, I mean, I don't know. Yeah, I think I answered the question. There's a lot I could say, but I have a hard time saying to anybody, this is what you should do, or this is how it works, or this is how I did it, because it's like, okay, so what am I gonna tell you? Like the real story, like, is be really broke, get a job that your first job where you actually make enough money that like you're okay, like before coding, so you're not super stressed out all the time about money. And then also when you get that job, make sure that it's at a what was I doing? I was selling cell phones. Okay. And so sell cell phones at a cell phone store, and make sure that you have enough business that you make money, but not too much, so that you can actually spend at least half of your day at the office coding. And then in 12 months, you can become a developer. And I think that's what's funny about people and all of the things that people try to say, oh, this is how you should do it or whatever. It's like there's so many different subjective factors involved that it's impossible to say, oh, this is the way. This is how this is what works. Like, how am I supposed to know what works for somebody else? I have no clue. That's just like how I did it, but like that's not applicable to anybody. And also, by the way, make sure that it's during a market time that's like very amenable to self-taught developers, and where people just need headcount, so they don't even care whether you have a degree or not, or whether you're good or not. You know? So I don't know. I mean, that's why the only advice in some ways, and I don't really consider it advice, I think it's just basic common sense, is like, look what jobs are available. Learn those skills somehow, you know? Like, maybe you'll get a job. Maybe you won't. I don't know. Yeah. Good times. Let's see. So here is our priority queue min heap. Okay, so let's go into our algorithm visualizer. I did not build this. This is just somebody's college project. Some undergrad or grad student probably made this as part of their research and got college credit for it. But it's pretty cool. I like it. It's simple. I don't know if this is popular. Like, min heaps are popular, but this visualization tool, I don't think it's popular. I don't know if it is. I just found it on the internet and I liked it. I think it's like simple enough, but also goes through all of the information that you really need. Okay, so the min heap visualization kind of gives away how we actually implement this, but I still think they did a really good job, because their job is to visualize it, not to test whether you know how to implement it. But we use this for a binary search tree, and it ended up being very helpful, so we're going to continue using it here. So you have an insert, and it's going to build a tree. Oh yeah, this is what I'll do. We're going to just, no, it's actually more confusing. You can do this build heap thing and it builds a huge one for you, but it doesn't actually illustrate things very well. So we'll just start with this. So we'll do keep building, purposely using some larger numbers. Okay, so here's a basic thing. I know you guys can't quite see everything, but if I show you the rest of the tree, then you can't see the other visualization. So it just is what it is. I guess, let's see. I could try. I don't know what's better. I think it's better for you guys to be able to see it. Like, we could go there. And it just hides a little bit. Sure, we'll try that one. 1 second before I get into this. Nope, nothing that matters. Okay. So here's a basic min heap. I also inserted these numbers in a way that didn't require the min heap to do anything, so that it didn't distract us with visualizations. But basically you have your min at the top as your root node, and you see this is drawn as a binary tree. And since I'm using dark mode, you guys might not be able to actually see the contrast that well, but you probably can see it a little bit. But you get the basic idea. So it's basically a binary tree. You have these two, and at each point, the only thing we care about is that everything below it is less than, right? So the good thing is that you know that this is, you know, it's true here, right? 145 and 300 are less than 50, 101 and 150 are less than 100. I could have done something that would have made this even more, you could say, confusing. Let's see if I can make this work. No, I can't. It's fine. All right. Because this makes sense. The main thing I wanted to illustrate is that over here we could have, over here we could actually have something like 75. And even though 75 is less than 100, it's still more than 50. And that's perfectly valid, right? That doesn't matter. So if I rebuilt this example, I'd probably want this to be 75 just to make that example really clear, because it demonstrates that the relationship only has to do with the parent and the children, not anything laterally. So that's it. So we have insert. We didn't do any special inserts. We could if we want. So let's do an insert of a number that we know is smaller than all these other things. I guess we could do a 75, because it will actually give us a little bit of what I was talking about. Yeah, that's nice. So we have 75 over here. Obviously 75 is less than 100, but it doesn't matter. They have no relationship in this min heap. So what did we do with 75? What we did is we actually inserted it. Our insertion point was at our first available slot. And that is because you insert things in a min heap in a perfectly balanced way. So you're just gonna fill each level every single time. And what actually happens is, instead of trying to find the place where you should insert it based on its value, you just insert it at the bottom and then you bubble it up. So technically insertion, at worst case, right, insertion could be O log n, right? Because we could end up going up half of our tree to make sure that were there. But I believe the way that it is, I don't know if they just determine it to be O log n in general, or if it's constant time in general. Since I wrote it down as constant, I should probably find that out. I forget that. Let me look. Okay. Let's start with ChatGPT. Why not? Psychology behind decision making? Just kidding. All right. What? Nope. Did not mean to hit that. My hand was in the wrong place. What is the time complexity of insertion in a binary, not binary search tree, in a Min Heap? We've been on binary search trees so long, I forget that anything else exists. Okay, so it is O log n. That makes sense. And then deletion, I guess you could say, because it requires okay, that makes sense. So they're both O log n, insertion and deletion. All right. Lied. Classic me lying. Now that I thought through it and thought about the time complexity, I knew I was wrong. So it makes sense. So even though the actual pop and push is constant time, right? It's maintaining the tree is O log n, because you actually have to either heapify up or heapify down. All right, good times. So yeah, that's the basics of our Min Heap. And this also kind of gives away one of the implementation details, which is, why is this all just shown as if it's an indexable, an indexed array-like data structure? Yeah. I think we'll find out. But let's go ahead and click remove smallest just for fun, just to go over that. And there you go. So remove smallest ended up putting 145 at the top, and then it actually ended up heapifying that down to the correct place. So that is a Min Heap, to ensure that our smallest element is always on top, and that's what matters the most. It's called a priority queue because in this case, your heap condition specifies your priority. So in this case, you want to say, I always want to get the min element first. So maybe you have a complex data structure, and that min element might actually be the time stamp of when it was inserted. Like that could be what you have your condition on, and so you just want to always get the thing that has the latest timestamp, you could say, or you could say earliest timestamp, right? So that would be like an example of getting a first in, first out queue, you know, but you know, first in where you don't necessarily control everybody that's putting in there. So if you had like multiple people inserting into this queue, you know, you'd have a potential to maintain priority or whatever, with multiple insertions. It's an idea. Okay. All right. So it's giving me this error just because we haven't written anything, and I used a doc string, and so it's saying like you have to write something, otherwise this doesn't mean anything to me. I can't be a doc string for nothing. Okay, so our priority queue, we're actually just going to use a vec underneath, which is perfectly fine. We could use a vec dequeue because a vec dequeue gives us both front and back O of one time. So that might actually be a better data structure to use. I call it a vec dequeue. I don't know if other people say vec dec. I don't know. I call it a vec dequeue. So in our priority queue, we actually would just have a private queue, and we can let's just use a vec dec. Why not? I've never used one before, so that sounds fun. So there's our vec dec there. That's right, vec dec is not imported by default, so let's import it. LSP, are you alive? You are alive! It's alive! Okay. Nice. You might be tempted to use like a linked list or something along those lines for or a doubly linked list for something like this, but it would be bad because you need something that's indexed. If you don't have something that's indexed, then you're going to be in a world of hurt. So that's why we're going to use a vec dec. If you were doing this in another language, or you're doing this on a whiteboard, say you're using JavaScript or something, like using a JavaScript array would be fine. Using a vec would be fine. Using an array, the standard array, growable array list data type in your ecosystem would be fine. I'm just going to use a vec dec because it actually has guarantees that will make this performant based on what I know I'm going to need to do. So that's why we're doing that. Okay, so there's our struct priority queue. There's a couple things I know that we're going to need because there is to make it simpler. Let me think. Not to make it simpler, but no matter what, the T that we accept for our priority queue is gonna have to be orderable, right? There's got to be a it has to support comparative operators, which is what we're going to be using in order to heapify up and heapify down, right? So that's one of the things that we know we're gonna need right off the bat. Okay, so let's do the easy thing, and we're gonna say new, and this is just going to be a priority queue. Right, forgot about the return, slightly important. All right. It already hates me for some reason. Oh, it's because I used 4. Nice. there's no trait here. We don't need the keyword for. It's just new. It's just our priority queue. Okay. So on new, all we're gonna do is create our vec deck. I guess we'll call it a vec deck. One less syllable for me to have to pronounce. So the vec deck's going to handle all of our underlying memory for us. We're not gonna have to really think about it. We could use the ring buffer. Like a vec deck is a growable ring buffer. We actually implemented a ring buffer already, but our ring buffer is not growable. So that could still be useful in some use cases where a priority queue just overwrites the oldest value. But in this case, we don't want that limitation. So we'll leave it like that. I think for now, instead of saying push and pop, I'm actually just gonna say, I still don't know what I want to call it. Okay, we'll ask ChatGPT. We'll ask ChatGPT. What is, wait, no, we need a new chat. People tell me it behaves better if you get a new chat every time. All right, what is a common interface for a Min Heap? Insertion, removal, peak. Okay. Yeah. Let's see. Is there a Min Heap in the Rust standard library? I don't actually know the answer to this. No, don't tell me how to do it. Don't do it. All right. I knew they were going to do that. All right. Let's clear that out so we don't read the code. All right. So let's use a vec deck. I think I'm just going to call it remove and insert. Nah, pop is fine. I guess we'll call it pop. Pop from the queue. Yeah, that's fine. I guess we can call it pop and push. It's usually what push is gonna return unit. Okay. And we might do peak. We could. It's not like it would be hard. Goodness. Okay. So our pop and our push are going to require a mutable reference to self, and our peak just requires a reference to self. That's easy enough. I guess it makes sense to start with push, since, you know, we can't test the other ones until we actually have elements in our queue. So let's try this. So push is going to require a value of t. And where do we want to start? We want to start with actually just pushing that value on. So with vectq, I think the method is pushed back. So let's start with that. Self.q.pushback value. I believe that is what it would be. Appends an element to the back of the deck. Okay. And it doesn't return anything. That's fine. So yeah, what we can do before this is we can say let I equals self.q.len. And even though we don't have to insert it with I, which we could, I'm pretty sure that our vectq, like we could do that, where we just say self.q I equals value, but that seems like a good way to get bugs in general. I mean, we know that it's going to work, but it just seems like a bad idea. If I can just use this method, I would prefer that. So we know that the length of our queue, our underlying queue, is going to be the index of the element that we just inserted. So once we do that, we're going to want to heapify up basically from I. So I think what we're going to do is probably implement a method called heapify up. And we'll just pass it that I. So that tells us that our heapify up method is going to take, we'll put it down. Where do we want to put it? It doesn't really matter, but sure, we'll put it down here. I think I want to put peak above pop because it's going to be simple. The implementation will not be difficult on that one, and so it won't have a lot of context that we would want. Okay. So let's say heapify up, and that's going to take a mutable reference to self and the index, which is a usize, and return nothing. Since push doesn't return anything, we can actually take off the to-do. Let's just think about if there's anything else we need to do besides the actual heapify up implementation. I don't think so. I think that should basically cover it. Okay. So we have some calculations to get parent, etc. Based on an index. So since we have a tree-like structure that is actually implemented as an index-based array, essentially, an index-based structure, let's go to our visualization real quick. What we have to code is It is interesting. I wonder, like, this is probably something somebody that has a CS degree might know, but I wonder why here on 0 they represent that with negative infinity, and then they go here. There must be a reason with how they actually implement this. It's probably to make the calculation of child to parent to child and child to parent easier in some language. I don't think that we're going to need to do like an offset. Like we don't need. I think we're going to be fine with a zero-based index, but I guess we'll find out. Yeah, interesting. Yeah, we'll find out. Okay, so let's see. This is just a matter of calculating parent and child based on index. If I remember right, you can get the left and the right. So we're going up. So we don't exactly have to think about it. Well, we do, because we have to compare it to the one right next to it as well, if I remember right. So we're going to have to think about all of those considerations. Okay, so let's just talk about what we're going to do. Usually helps if I just write it out in a comment. So if we're heapifying up, like let's talk through it this way. So say we added 30. We know 30 is minimum here. So if we added 30, we would add it right here underneath 145. We would then want to compare 30 to 145 and know that it is less than, right? We would then go up and compare that 30 is less than 75. So if 30 isn't less than 145, then we can leave it where it is. Obviously it is less. So we go up and we switch 30 and 145. And then we say, is 30 less than 75? If it is, we can switch 30 and 75. We know that since 30 is less than 75, then it also has to be less than whatever number this is over here. The only time I think we're going to have to worry about this is actually when we're heapifying down, if I remember right. But we'll see when we get there. And then we would compare 30 to 50. So in this case, all we have to do is care about the parent. We don't have to care about any of its siblings. I don't know if heapify down we have to care about siblings. We'll figure that out when we get there. I need to take my sweater off. 1 second. Yeah, that's what I thought. It's just funny because like there's someone that just likes jumping into Rust streams and asking random questions, but he doesn't like following anybody. and it's not like it matters. It's not like people have to follow, but like he's probably jumped in my stream like 10 times, asked a question, and then probably left once he realized there's like nothing I'm gonna really do for him. I don't know, just odd behavior. There's not really a point, just feels like odd behavior to me, but that's fine. Heapify up. Right, so what are we doing? We already have the inserted item. We know the index that it's inserted at. And so then we're just going to compare to parent recursively and swap out. Compare to parent and maybe swap. Okay, so that shouldn't be too hard. So basically we would want something like this, and our parent index is what? Let's talk about it. If we're at 145, 145 is actually, we'll have to just kind of subtract 1 in our heads from all of these. So 145 is actually at index 3. There's not another 145, right? Yeah. So 145 is at index 3. If we want to get 75, which is at index 1 from 3, then that calculation, if I remember correctly, and this is somewhat from like learning this at some point, so it's not like I'm this smart. If I remember correctly, it is just 3 divided by 2. Let me think about this. So this is 3. 3 divided by 2 is 1.5, but in a real language it's 1. We're not casting things. So 3 divided by 2 is 1. Okay. Yeah. And then what about 4? 4, which is here. 4 divided by 2 is 2. Okay. Give me a second. I think this might be why they have it the way that they do. I need to just think about this. Because here, the way they have it, 4 divided by 2 minus 1. No, that would be 1. No, that doesn't help either. If I remember right, the calculation is actually I divided by 2 minus 1. Like this. Oh my god, if I knew how to type. But let's see if that would actually work out. So this is 0, this is 1. 1 divided by 2. What does 1 divided by 2 equal in real integer languages? This is what happens when you use a dynamic language at work. You don't know obvious questions. Let's open up iRust real quick. I don't know what it's going to do. Well, if I knew how to type numbers again, we would be better off. Okay, 1 divided by 2 is 0. So it basically like floors it. Okay. 2 divided by 2 is 1. I knew that answer, but I just had to think through it. So 1 divided by 2 minus 1 Yeah. Okay. I just needed to see that happen. So obviously 2 divided by 2 minus 1 works. Wait, why are you saying this is going to not work? No, you're... Oh god. This REPL is not very good, in case you were wondering. Let's restart it. 2 divided by 2. Oh no, no, that was my fault. That was my fault. I had my parentheses wrong. That was me. It wasn't the REPL. 2 divided by 2 minus 1, 0, obviously. 1 divided by 2 minus 1. Yeah, the thing is, like, we could do a special case, I guess, for that. Okay, let's work out a different example. Just to make sure that the logic makes sense. Like, obviously I could do a special case for the 1 divided by 2. I could be like, you know, if I divided by 2 equals 1 or equals 0, then 0. But I don't know. Let's make sure that the logic works everywhere else before we have that one special case. So this is 0, 1, 2, 3, 4, 5, 6. Okay. So 3 divided by 2 should be 1. 3 divided by 2 is 1. Okay. Huh. Weird. Thanks. My daughter's just throwing money at me. How about it? Okay. Is it just I divided by 2 and I'm... No, that won't work. It won't work in the right-hand case. I mean, I could know if it was based on if it was odd or even, right? So if I use 0-based indexing and I don't do anything dumb, I could say that if it's positive and odd, we know it's on the right-hand side, right? I mean, yeah. Okay, well, we have our first base case, actually, which is when there's no parent. And that's if I equals 0. So let's just write that out first. If I equals 0, then we don't have to do anything. We can just return. Else. And I know that's not how I'd actually write it. It's just easier for me to think through. Okay. We know that much. Let's see. So 150 has index 6. 6 divided by 2 would give us index 2. 101 with index 5 be 6 divided by 2. That's an interesting idea. Like, what if we did... Okay. What if we did 5 divided by 2? Well, let's just work through this. 5 divided by 2 is 2. So then if we did 5 modulo 2, really? Took that long to do a modulo? So maybe the correct answer is 5 divided by 2 plus 5 modulo 2. And that would give us 3. And 100, oh no, 100 is already 3. There, which is incorrect. We should want 2. Oh, so 5 divided by 2 gives us the right answer. Oh, why is this so annoying? Okay. Alright, I think I need to do the heapified down calculation and not the actual function, but just like how you get the child, because to make sure that I am on the right track. This is very much on brand right now. So if you wanted to get the left child, it should be I times 2 plus 1 and if you wanted to get the right child, it's I times 2 plus 2. And let's just work that out real quick. 0 times 2 plus 1 is 1, times 2 plus 2 is 2. 1 times 2 is 2, plus 1 is 3, plus 2 is 4. And over here, 2 times 2 is 4, plus 1 is 5, plus 2 is 7. Okay, that logic works out. So with that logic, this is left, and this is right. Okay, so then to get the parent from a left child would be the reverse operation. And so what would we say? If we already did this. Let's just take the easy example and say 1. And 1 divided by 2 is 0. 3 divided by 2 is 1. Right, so in a real language, the left is just I divided by 2. And the right is to get the parent from the left is I divided by 2. And the right is I divided by 2 minus 1. I think that's correct. Okay. Now I kind of see... I think I see why they would do it the way that they do it. Let's see if I'm right. If 2 divided by 2 is 1, that's correct. 3 divided by 2 is also 1. So that's the advantage of putting like a filler in 0, is that at each step then, like here 6 divided by 2 equals 3, and 7 divided by 2 also equals 3. That's the advantage of having a filler in the 0. I see now why they do it that way. So we have a couple options. We could actually just put a default value into the first index. We could do that. We could also, what's the other option? Thinking through this. If that's a 1, 1 divided by 2 is 0. That's correct. That's 2. 2 divided by 2 is 1 minus 1. It's all modulo. Yeah, I don't know. I guess we could do that. We just have to decide what is our filler. It's either that or we only insert. I guess that's actually the other option. Is let's see. We could do vecdq new. And we could do a capacity of, like, we could do vecdec with capacity of 1 and then put right, and then not actually, oh, that's what I was thinking actually. No, that's what I was thinking. What I was thinking is we could actually, oh no, no matter what, we'd need a trash value in there. So basically our options are to require default on T, which is not the worst thing. And then on our vecdec, we would do something like this. We'd go vecdec new. Actually, we say with capacity. One. And then we'd say q.pushback T default. I didn't declare it as mutable. Let's see what that requires then. Yeah, so then for our child calculations, what this does is that our left child is just I times 2, and then our right value is I times 2 plus 1. Okay. And then our parent value, our parent calculation for both of them becomes I divided by 2, which definitely makes things simpler. Got to fix this. Okay, so it will require to only use T's that are default, but it's something. Okay, I think I'm happy with that. It'll also make the visualization easier since we're actually following the same example that they did. What's interesting is this is somewhat based off of Prime's DSA course, and I don't remember him doing this. I specifically don't remember, but it's been a while since I watched the whole thing, and I don't remember him doing it this way. So it'll be interesting to read, maybe I'll watch that later to understand. Well, after we'll finish our implementation. I don't think it'll take that long. And then I'll watch the way he does it, and then we'll compare what we like better. So a lot of times you wouldn't care about the length, but I kind of want to, only for this reason. Which is that self.q.len -1 is our actual length here. So yeah, because of the way we do this, we know that it already has one. We know that we'll be okay. The only thing that's a little like, you know, maybe not great about using the default implementation, the default there, is that we are requiring allocation even with no elements. I could have, like, I think I could use a dangling pointer instead. But we won't deal with that. We'll just leave it as default for now. We might go back to it. Okay, so there's len, mostly just so that we understand that the length of our priority queue is always going to be our underlying queue's length -1, because we are kind of faking a 1 based index here for our min heap to make our calculation easier. So we don't have as much if branching and all that kind of stuff. Okay, so let's think about this. Yeah, so then what I can actually do here is say let parent equals I divided by 2. And then it's not the actual parent, of course, so let's make that obvious. It's our parent index, and we'll just say if parent index equals 0, then we're done. We don't need to do anything. So actually what we can do now, since we know we don't need to do anything in this case, we're just going to say not equals, and then we won't have an else branch. So let's get rid of that and go here. Okay, sweet. You're just saying you can't put a creative thought into our priority queue right now, Purplish? Come on, man. Just forget about the View 2 app. Don't worry about work, and we'll just do this priority queue. It's much more important. No, I feel you. No worries. Okay, so if parent does not equal If parent index does not equal 0, then we can go ahead and get our parent. Let me think how I want to do that. I think mostly we're just going to compare anyway. And since our vectq implements index, pretty darn sure it does, we should be able to just say self.q so if self.q I is second, Allison got second. Nice. Good work, Allison. Hope you're doing well. It's important. I mean, you definitely... Wow, I don't know why that peaked when I said important. That was some weird shit going on here. You definitely got rewarded for your valiant effort in redeeming 2 channel points or 1 channel point or whatever it is. Good times. If self.qi is less than self.q parent I, then we swap them. Otherwise, we do nothing. So if the parent is greater than us, we don't have to worry about anything, and we're done. If I meant if the parent is less than us, you know, we're getting there. So if self.qi, self.q parent I, okay. Then we say let parent equals, let me see, what order do I want to do this in? We basically just have to have a temporary value, right? Let self equals self.q. Oh, I actually think vectq might have a swap method. Let's see if it does. I know vec has a swap method. I wonder if vectq does. Vectec. Nice. Let's see if this does exactly what we want. Swaps elements at indices almost feels like cheating. Oh, it feels so much like cheating. Oh, it's just having an actual nice interface. I mean, it's not like swap is that hard to implement, but the reason that I was not looking forward to implementing this is mostly because of like I just felt like it was going to end up being annoying from a borrow checking perspective. Okay, so it doesn't really matter which way we do it. The swap is a swap. So all we have to do then is say, oh, because things have been so hard, like for our binary search tree, when it's really easy, I just feel like I'm doing something wrong. Like, this is too easy. But we'll find out in our tests on just how easy it actually is. Okay. Self.q.swap I, parent I. Yep, that looks good. And then we're gonna say self.heapify up using our parent I. Okay. And so there's 2 base cases here, basically. The first base case is we reached our root, right? Okay. The other base case is that I mean for our recursion here, by the way. The other base case is that our parent is actually less than ourself, and then we're done. Okay, so here's heapify up. We'll find out if we got it right. Let's write some tests finally. Mod tests. Use super star. I forgot to put the whole config test thing in there. It was like this config test. I think that's how that works. Test function insert works. Oh, I forgot. I called it push, didn't I? I don't remember what I called it now. I did call it push. What's nice is that our debug print will just be like kind of nice right away. So that's gonna be nice. Look at that type inference. I think I did that on all the other ones where I actually specified the type and it was not, I mean, I actually specified it as usize and it's just assuming it's an I32 and that's fine with me. I don't really care. Look which one it is. Okay, so 50 is our first element. Let's just do a 75. Now, of course, what's funny is, let's do 100, and then let's do 30. Okay, and let's go ahead and clear out our Min Heap that we did, so that we can follow along here. 50, 75, 100. Okay, we'll start there. How about it? So we don't really have like a nice way of doing this. We could, because we know our internal implementation and because we have private access, we could like check the index of each thing. I don't know. It's like, the thing is, if you're using internal implementation details in your unit test, then, and I just mean more as like a principle, obviously for a hobby project it doesn't really matter, but like it's kind of a bad unit test because I might want to change the internal implementation and then my unit test shouldn't fail just because I changed the implementation, right? It's kind of the point. So what we're gonna do is just do a debug print on PQ at each step. Actually, we'll just go there, there, and there. And we will have to derive debug. Dervice. Do you like to dervice things? Derive. Debug. Okay, cool. And we'll move over to our terminal and get out of this REPL to say cargo test. What did I say? Pushworks. Pushworks. No, whoops, no capture. I think it's like that. Nice. Okay, So we have 0, which is our default, 50, 50, 75, 100, and 30, 50, 175. That looks right. Now, it might not look right in this printout because 75 being the last value and being smaller than 100 probably looks wrong. But if we do it on here, we should see hopefully the same thing. Unless I'm thinking about this wrong. No, yeah, that's what I thought it did. Okay, good. So you see, like here, we have 30, 50, 175. Nice. How about that? Okay. So, pop is actually pretty easy. I guess we could implement peak, and that would actually give us some testability that Min Heap is working. It's not going to show us our full queue, of course, but we could do this, which would be nice. So if we wanted to do peak, we should be able to actually just return self.queue. I want to say we can do I, but we'll find out. It might not work the way that I'm thinking about it. Oh, I said I meant one. I meant a literal one. Okay, yeah. Yeah, okay, it returned the type itself. That's what I was thinking. So in that case, I could... What can I do here? I have a couple options. I could do... Oh, right, I can do the whole slice. No, you can't do slice on a vec deck. If I was using a vec instead of a vec deck, I could do a slice representation of that, but I can't do that. So I could do like the range syntax and get that. I wonder if vec deck actually gives range. Like if I do this, 1 dot equals 1. I think that's how it works, right? No, I'm forgetting the range syntax. Maybe it is like that. Nope. I think it just doesn't actually. Expected type use size, found struct. Okay, yeah, so it just doesn't implement index for a range on vecdeck, which is not surprising based on the underlying data structure. Okay, so then, since we can't do that, what we can do is just say an and the reason we can do that is because the lifetime's derived from self. So that's fine. We can do that. So then we can make our test a little bit better in that we can, let's not worry about this debug print, but I'll keep the 1 at 100 to make sure we don't break anything as we go along. And we can say pq.peak. Might help if I actually did a little assert here. And oh yeah, peak actually needs to return an optional. Oh my gosh, can't believe I forgot about that. Hilarious. Because it might be empty. Like that parentheses instead of a optional reference to T. And this is simply if self.q.len is greater than 0, then this, else none. Right. Might help if we wrote the word sum, probably. There we go. That'll help. That'll help things. All right. So let's. It's really funny. It's a very me thing to do. PQ.peak and so that should still be that. And if we do it here, we should get a none. Okay, let's see if those tests pass. No, they don't. What did I do wrong? Oh, wait. No, that's still right. Sum n50. Okay, okay. Panicked at out of bounds access? Oh, did I do something wrong up here? Did I never actually... No, that should be right. Huh. Huh. Minecraft villager time. Okay. Let's see. Let's run it over here with no capture and see if we... It's that very first one. So that just means that I messed up this. Oh god, I did self.q.len. I meant to do self.len. Duh. There we go. Dumb mistakes. Look at me using options. Yep. Like a real developer. Like a real rusty developer. Okay. So push appears to work. Heapify up appears to work. That's cool. Okay, so now we just have pop. So pop is simple to start with, in that we are just going to say let v equals let me see how I actually want to do those. Yeah, that's the right way to do it. Okay, so I can actually say self.q.popFront. Oh, I don't want to pop front. So we know it's going to be 1 every time. We can't use pop front because right, we can't use pop front because our 0 is actually just a trash value, just garbage, just to make our index calculations easier. So we have to do a remove at, and I don't remember what that's called, but I'm pretty sure I am pretty sure it's called remove. Okay. So we're just going to remove at 1. And this should just make sure removes and returns the element at index from the deck. Which end is closer to the removal point will be moved to make room. Okay. This is good. So pop also returns an option, except it has an owned T. Okay, so the thing is, we can actually, we can remove this and just return the V. Since it's already an option of T, that'll work for us. And at that point, we don't really care about that V anywhere else. Now, of course, if it is none, actually, whether that is none or not, yeah, okay. No matter what, we're actually going to do a self.len check for our heapify down. So I believe we're going to start this as if self.len is greater than 0, and whether or not that was whether or not there was any element there or not, that if check should be valid. Because if we had 0 elements, that'll return 0, and V will just be none. If we had 1 element, we just removed it, and our length will be 0, and we'll return that option. And in both of those cases, we don't have anything to heapify down, right? So when we heapify down, let me think. Yeah, we'll still just specify an index. Yeah, okay. And we can just heapify down. And our starting index to heapify down is going to be 1. Okay. So here's heapify down. So yeah, the difference with heapify down is that we have to, of course, compare it to both of its children. We can't just compare it to one. So that will be one of the differences. So let's see. What do we want to do? Maybe fill out this queue a little bit more so we can kind of talk about what should happen. So let's just go with something like this. And yeah, that's fine for now. Okay. So if we deleted 30, what's going to happen? 50 would become our de facto root. And that's more because of the order here. And then we would take that 50 and heapify down. We would say, is 50 greater than, ooh, that is interesting. Like, how does that part work? Because if we just fuck up our data structure, then 50, this would be 3475, and then this would be 6500 underneath. So I might be missing a key element of how to actually do this part. Let's just delete some things and see what happens. So if we delete 30, oh, that's right. I forgot what it does. That was fast. I don't know if you guys saw it. Basically what happens is it takes the last element and puts it up here and then heapifies it down. So what we should see is 65 go up here, and then it's going to go back down to here. Let's see, it'll go down. 50 will replace 65. Let's see. Let's do it again. So we'll remove smallest 34. We get 65. It replaces 50 with 65. So it maintains the structure that way. So it's structure preserving. That makes sense, because it's like, it's gonna, if we just completely remove it, it's just going to fuck everything up, right? And that's not what we want. So we don't want to do self.cute or remove there. We want to do something smarter. I don't know for sure if I'm going to finish this. We'll see. I have kind of a hard stop at 4:30. I think I want to stand for a bit. Let's stand up. Let's stretch, you know? We'll do it together. The first time you've seen a Min Heap or me standing up? All right. Oh yeah, my back's pretty sore. I did my exercises today. I didn't stand up. I mean, I didn't sit for that long today, but oh well. My back's a little sore. Who knows? It's just what happens when you get old, guys. Okay. What were we doing? Oh yeah, we don't want to remove. We're actually going to do another swap, and then we're going to pop from the back. So let's do it that way. So there's a couple things that we have to do. Let me think about it. In this case, we do kind of care, because I think swap is going to complain if did not mean to type 72. I meant to type 27. Okay. I think swap is going to complain if I and J are out of bounds, right? Typically how these things work. No, not what I meant to do. Let's look at the whole doc buffer. Yeah, panics if either index is out of bounds. That's what I expected. Okay, so in this case, we actually do have to check len first. which is fine. I'm just trying to decide where I want to do it. I mean, we could do it here, I guess. I think I'm getting too distracted from my code. I think I just want to erase it all. I'm getting too distracted by what I've already written. Let's detach ourselves from the code we have already written so we can write better code. Or code that actually works, you know. That's the definition of better code in this case. Okay, so let's just start with ifs, because it'll help us clarify each of our cases. So if self.len equals 0, we know that there's nothing to pop, right? Else if self.len equals 1, we're just going naive at this point. Then in that case we can just do a self.q.remove. No, it's pop front, isn't it? No, remove 1. Yeah, that's what we want. Except we want to return it. Else self.q.swap. I'm going to swap 1 with the back. So let's just get our eye that way. Let end equals self.len -1. We could say last end. It doesn't really matter. Okay, self.q.swap doesn't return anything. Not surprised. Because what would you want to return if you're swapping two values? I don't know. Which value do you want to return? It's hard to know. So then, at that point, what we could do is say let v equals self.q dot pop back, because we just moved that thing to the end. So we're doing like one extra operation in some ways, you could say. I could, and it's mostly because it's the easiest way I can think of bypassing the borrow checker while preserving the structure. And I mean, at the end of the day, it is, I believe swap is actually just a single mem copy. So it's not the most expensive thing. Well, I guess it would have to be 2, right? I don't remember right now, but it's fine. It's not super expensive. It's still just like quick memory manipulation. It's not anything big. we still have constant time access to all these things, so we shouldn't be doing anything too onerous here. And then we would say heapify down, and then we would finally return our option of t. Yeah, heapify down needs an index to start with by design, and that's going to be 1. Okay. It's not so bad. We just have to get heapify down right. Okay. Not so bad. So let's see where we're at. So heapify down, we're going to compare to both children. Not necessarily. That's actually wrong. What we're going to do is compare to left, then compare to right, etc. I'm not going to write out the rest of it because I think it's actually going to be easier to just code it, but we'll find out. Okay. So here we're going to have a lot more optional things. We have a couple options of what we could do. I think our self.q implements a get, which will give us an option back if something exists at that index. So we'll see if that's true. If it does, that's going to be helpful. Just making sure I understand what I'm doing here. I think so. I think we're good. Yeah, I mean, I see some way I could make this simpler, but it's fine. It's fine for now. Okay, so no, we can do this simpler than this. We know that the index exists where we're at. So that's true. At least at 1 we do. Because we did a self.len equals 1. Yeah, okay. Let's just keep working it out. Okay, let's just do this to start with. I think this is a thing. Hey, look at that. Look at Rust coming through for us. Okay, so to get our left, it's just I times 2. So that's what we're going to put in there. And then to get a right, it's I times 2 plus 1. And I just did different spacing to trigger people. Just kidding. Kind of kidding. Okay. Yay. Yay, options. All right. And so this gives us option and t's, which is all that we need. Now, I'm pretty sure I cannot compare within the option. I think I'm going to have to get the values out of it, but I can't remember right now. I don't think option implements partial ORed if t is partial ORed. I can't remember, but we'll just try it. Okay, Let's say, I mean, we could try this, right? We'll just get options for everybody. Options for everyone. Okay. And then we're just going to say if L is less than V, then we're going to do something. Else, if R is less than V, then we're going to do something. Otherwise, we're done. We don't have anything to do. Our element's in the place that it's supposed to be. So this should compile since I'm not actually returning anything, and let us know if option is nice to us. It does seem like option does have partial ORed. That's pretty cool, since T is partial ORed. That's smart. I don't know if I knew that before this moment. That makes this a lot nicer. Because we can just keep it at the get in order to have these wrapped as optionals. Let me see. We might not actually want that, because if they're none, so that's the other part. First of all, if L is none, then we know that right is none. That's kind of the part of our structure that we know. I don't know if we really need to encode that somewhere, but we could encode it somewhere if we wanted to. We could just do like a master match statement on all of this. I don't know. There's a lot of options, and I'm kind of getting lost in them. Okay. Let's see what happens with none. Let's just do let's look in the REPL real quick and see what happens with none. So if I say sum 5 is less than sum 10, should be true. Okay. And if I say none is less than sum 10, I would kind of ideally that would be false. Oh, it's true. Okay. Interesting. Only reason I'm saying ideally it would be false is because it would help me in this particular this one particular thing I'm implementing to not have to do another check, but that's okay. It'll make it more expressive. Okay. I think matching might actually be the nicest thing to do here. So I think that's what I'm gonna do. Let's do a match on VL and R. Match VLR. Okay. If V is none, like, we kind of have problems in how we called this most likely. I don't know exactly how I want to do that. Okay. But basically, if any of our values are none, we want to return none. We could make this less lines of code another way, but that's okay. The thing is, hey Scottish Trio, how's it going? Thanks for dropping by. How's your evening? your work week, I imagine, is over. So you're now going into your weekend. Hopefully. It is Friday, Allison. I know. I don't have a standard work week, so I lose track of days. Let's be real. I'd lose track of days no matter what, right? All right. Now this next conditional actually would never happen, but I'm just doing it from a completion, like being complete in my pattern matching standpoint. Yeah, right? Yeah. It's definitely like a classic ADHD thing too, for sure. But you know, I'm sure even the neurotypicals among us may feel that way. Oh God. Okay, then not until next Sunday. I read that wrong the first time. That's something. But you know, at least you get a rest. You going on holiday, or are you just for other reasons? Yeah, it's a weird match so far. I'll probably clean it up. But we'll see if I like this. We're just trying it out. Okay, so we're gonna shadow some V. We're gonna shadow V with V and L with L, and we're just gonna love it. We're gonna love that that's happening. If L is less than V, then we're gonna do something. Oh, that's cool. Yeah, that's great. I mean, I like stuff like that sometimes, you know. It sometimes works out for the better. I actually don't work on Thursdays, and I work on Sundays instead. And that's just there's historical reasons for that, personal reasons, but now it's actually just something I like. Breaks up my week, and Sunday's so quiet because nobody else is working. Can kind of get shit done without anybody bothering me. And I like it. I like it personally. I like it more than a standard work week. Okay. So now that he did all this, yeah. I don't need any of these. I just had to write it out so I could think through it. Hey, what's that thing where something never happens? The just build or just learn thing is tiring. Yeah. For now, I'm just going to return unit, because I'm returning unit in all my other cases, and that's going to be fine. Yeah, I'm right there with you, Allison. I started streaming when I was contributing to this project called Atomic Data, and I really enjoyed that process of not having the mental burden and pressure in some ways of like deciding what I'm going to build, how I'm going to do it, and for there to be no stipulations on it, as well as no feedback on it. And I enjoyed the process of contributing to an open source project where that wasn't the case. So I don't know. It's an idea. You look at projects and find vulnerabilities in them. That's cool. It sounds like you might be more on the OPSI as I say it, which might sound odd if, I mean, I know you're might be harder for international folks, and I mostly mean people that don't speak English as their first language, but I don't know if that's a hard word. Anyway, my point is, like, are you more like on the DevOps side? That's really what I mean. I call it OPSI. I don't know why. Like OPSY. It's just like it's my cute pet name for ops. OPSI. All right. I think what I want to do. Adorbs, such a great name. There's those little moments where the queer really comes out, and that's one of them. Not that straight people can't have nice names for things. Don't get me wrong. You guys can still say cute names, okay? Don't worry. But yeah, anyway. Good jokes. Okay. Don't have to be queer to have cute names for things. There's plenty of cute names to go around. Okay. Some V, some L underscore. If L is less than V, okay, then we just want to heapify down. Now, the part that I actually hate about this, now that I wrote it all out in a match statement, is that I don't have like LI and RI right here, and I'm gonna need them. You're a SOC analyst? Oh. Got it. No, that makes a lot of sense, Scottish. Yeah, I get it now. Oh god, it's 4:32. I was supposed to leave at 4:30. Okay, so let's just write out the logic of what we need to do next. That's my partner literally messaging me saying, so are you coming? Okay. Some V, some L. If L is less than V, right? All we have to do is swap the values and then go down T. Let's just think about this. Are we always going to go down L if L is less than V? No, we're not. And that's because we actually have to find the minimum. Oh, Michael, what are you doing with your life? Okay. Nope. Nice try, Michael. Nice try. Okay. This is what we need to fix then. Find min child. Compare. Find min child if min child is less than V. Swap with min child. Classic man-child moment. Yeah, that's easy. Okay, swap with Minchild. That's the right logic. Okay. That's where I had it wrong. It's not compare to left and compare to right. You have to compare to both of them. I could easily do this in probably 30 minutes or less and have this all working. But, you know, I gotta go. Museum is doing rest. Okay, let me see if anybody else pops up that I really, really care to raid. Not really. Okay, we can do Museum. Está bien. Raid Museum. Hopefully I spelled that name. Oh yeah, he disabled, or they disabled raids. I forgot about that. I forgot that they disabled raids. Oh, Kinran's going. We'll raid Kinran for real this time. Kinran __. There we go. And just tell him I had to leave. Because I'm literally going to raid him and drop. Because I'm already 5 minutes over. I'm supposed to be cooking dinner right now. Alright guys, thanks so much for hanging out. I'll see you on Sunday and we'll finish this up. Did that really not work? Did I type his username in wrong again? I'm pretty sure I didn't. Oh no, it worked. Okay, sick.